Okay, so we're going to look at multiplying rational functions. So we have two rational functions here, and essentially they're multiplied by each other, as the brackets represent. There's a couple ways we can do this. Usually we want to try to make it as simplified as possible. One of the ways we can do this is we can, because this is essentially, think of the idea of this being a fraction, the first part being like a over b, and the second part being times maybe c over d. Fraction rules state that we just multiply the top by the top and the bottom by the bottom, and that would be AC over BD in terms of our variables. Granted, in that example, that shows you this straightforward, we may be able to simplify stuff. Now, it doesn't mean it's wrong if we just go ahead and think of this like multiplying binomials. You know when they talk about FOIL, where you do the first, and then they do the inside, then we do the outside, and we do the last terms. Or you think of a rainbow method where you do all of them. You can do that, and you'll get a a trinomial that probably has about 4 terms to it. We might be able to simplify it into 3 terms. Maybe from there factor, we're not quite sure what we got. Or we can factor off the bat. And factoring off the bat might make things easier. We might be able to reduce some of the rational functions so that when we actually get into the multiplying part, it might be a little simpler to work with. We'll start that, and we'll do both ways because neither are wrong. They're just different forms. So in the first one, if we take a look, I can common factor out the value of x in both of these, just like I can common factor out y on the numerator for both. So when we go take a look at this, we have x times 1 minus x divided by y. I just put that in red so we saw we would common factor out 1 minus y squared. Okay, and the same idea in the other one. We're going to factor out y, x, and x. And we'll see if this helps us in terms of simplifying anything. Again, we'll get our y, and we'll get 1 plus y. And in our bottom, we'll get x times 1 plus x squared. Okay, so really all this says when we're multiplying, instead of doing the expansion like we had before, a multiplication question, and you'll see it commonly written when you have like a coefficient in a variable. If I have 3 times y, they just write it as 3y. They push the two terms together. I could distribute everything in, but I just factored. That's the opposite of what I really want to do. Instead, what I'm going to do is I'm just going to push these terms together, all of these. We're going to push them together so they're all above something. And then we're going to see if we can start reducing quickly. So we have an x, okay, and we have a 1 minus x, and we have y and 1 plus y. And I can change the order of these. A rule of multiplication, I believe it's called associative property. And what that means is you can multiply in any order. It doesn't really matter. You'll get the same answer. And if you're unsure about math rules, sometimes I put little things to test myself. Does 3 times 5 equal 15? Yeah. What about 5 times 3 in a different order? Yeah, it does. Well, that was 2. If you were to add a term in front and at the end, does that change it? Well, 2 times 3 is 6. Times 5 gives you 30. And if we do 5 times 3, that's 15 times 2. Still 30. So that's kind of showing the rule there that the associative property doesn't matter the order. So on the numerator, the bottom part, I'm just going to erase that. I'm going to actually change the order. I'm going to move our one variable terms to the very front. So I'll have y times x times 1 minus y squared times 1 plus x squared. And I just did that to show you that it can be put in different orders. What we can start doing now is we can start reducing values. I have a y on the bottom and the y on the top. And if you think of that like if y was the number 5 and I had 5 on the top and 5 on the bottom, well, they divide into the term that's 1, and 1 times anything doesn't change it. So sometimes people call it canceling out. It's really just creating a 1, but we can keep that concept of canceling things out. We can get rid of the y's, and we can get rid of both our x's. That works out really good. Now, our top and our bottom, they're not quite the same, though they look very similar. We have squareds here. So I'm going to rewrite this again and take a look at it. 1 minus x, 1 plus y, divided by 1 minus y squared, 1 plus x squared. When I quickly look at this, the top, there's nothing I can really do. This value on the bottom, I can't do anything, but this one is actually a difference of squares. So I can factor that again. And when I factor my difference of squares again, on the bottom, we'll leave the tops off 1 minus x, 1 plus y, divided by our difference of squares ends up being 1 plus y, 1 minus y. And maybe I should write that in blue. This is where we just expanded our difference of square, or I shouldn't say, sorry, not expanded, we just factored our difference of square from here. Okay, and then we still have the other term that is 1 plus x squared. And using that same concept, 1 plus y and 1 plus y, they also create the value of 1, so you could, I guess, call it again canceling out, and you're left with 1 minus x on top divided by 1 minus y and 1 plus x squared. Had this been a difference of squares, we could have canceled out and probably canceled out what was on top. And this is probably as simple as we can go in this question. I just want to quickly check something here. Finally, the last thing that we haven't done, and probably should have done right off the bat, was stating the restrictions in this question. So when we take a look, when we first factored here, and we had our values at the bottom, we essentially got to set each of these equal to 0. And the reason being with a rational function is anytime we take a rational function and we divide something by 0, it's going to be undefined. Okay, so we're going to have an undefined answer no matter what our x or y is above. So we have to make sure, since all of these are being multiplied by each other, that none of them essentially equal the value of 0. And you can kind of look at this as 4 different terms. Here's a term, here's a term, here's a term, and here's a term. What we can do to make sure none of them equal 0 is we can set each of these 4 terms I've just kind of laid out equal to 0 on the bottom. So I'll write them out again. Now I guess here on the side's good. And we'll do it in purple. So y times 1 minus y squared times our x times 1 plus x squared. Each of these cannot be equal to 0. So what we'll do is we'll split. We'll have 4 different answers. Y cannot equal 0. That one's already done for us. The next one states 1 minus y squared cannot equal 0. X cannot equal 0, so already 2 of the restrictions done right off the bat. And the last one here, and that squared should be inside, not on the outside, is 1 plus x squared cannot equal 0. So these 2 are already done. We finished both of them. That's 2 of our restrictions. Y and x can't be equal to 0. And our other one, we'll move 1 to the other side, and we'll get negative y squared cannot equal negative 1. We'll divide both by negative 1, so we'll get y squared cannot equal 1. And in order to isolate, we're going to square root both sides, and we're going to get y cannot equal plus or minus 1. And the same thing's going to happen probably on this side. Let's take a look. X squared cannot equal negative 1. And we actually can't find the square root of a negative, so there is no restriction in terms of that. And that makes sense because whether we have a positive value or a negative value, we're always going to get a positive number here, and 1 plus that will never equal 0. So there is no real restriction to work with that. So our only restrictions, if we were to list them out, is that y cannot equal negative 1, because that's in here, 0, and 1, and x cannot equal 0. So those are our 4 restrictions for this question.